Good afternoon, everyone. We're going to get started with our webinar in just a few moments. Okay, it is 2 o'clock now, so I am going to get started. Good afternoon. Thanks for joining us on our call today. My name is Nicole Van Wert-Quincy from Transcat, and I will be your moderator this afternoon. Our webinar topic is how to calibrate an RTD using a dry block calibrator. The topic is being presented by Travis Porter from Fluke Calibration. Travis has worked at Fluke Calibration in American Fork, Utah in a variety of capacities for the past 19 years, including customer service to technical support, and his current role is inside sales account manager. We expect today's presentation to last roughly 30 minutes, and then we'll answer any questions that have been submitted during the presentation. Anytime during the presentation, you can send questions through the question box to the right in your webinar controls. I also want to mention that the webinar is being recorded. Each of you will receive a follow-up email with a link to the recorded webinar and the slides of today's presentation. At this time, I'm going to turn it over to Travis.
All right, welcome everyone. Let's jump right in. I kind of bobbled through a couple of slides as Nicole was talking. So again, I've been around about 19 years in the industry. So let's just jump into it. Today, the agenda, we're going to talk about using a dry well calibrator to do a calibration with a prober sensor. So I'm going to do a quick review, basically dry block introduction, kind of some sources of error, kind of some solutions to consider for common errors and problems you might see in the process. I've got a couple of slides on calculating uncertainties that we'll touch on. That one can kind of be a little bit of a rabbit hole because there's many different ways to interpret the data. So some folks will do temperature to temperature, some are temperature to resistance, and when you do the temperature to resistance, there's several formulas that can be used, all that are which acceptable. We'll also kind of give you some options with odd shape probes and sizes, different temperatures, ranges and concerns. I'll touch on some liquid and glass because that's come up a few times over the years about using those in dry wells. And then we'll do the RTD example, and then just a quick kind of how to maintain dry blocks, which is good. And then just a summary, and then we'll hit the review. So let's get busy. Dry block introduction. So basically, what is a dry well? Well, it's kind of what it says there. It's a heat source. So you can think of them like an oven, but a very, very accurate oven. Most of them have some sort of a block assembly or insert that will heat or cool to a specific temperature. The accuracies on dry wells can range from several degrees to very accurate, to tenths of degrees. Again, the block design, some of them are fixed, some of them have what they call a block insert design where one is removable and exchangeable. Some of the pros of going this route with a heat source is, again, you're not dealing with any fluids like a bath, so they're obviously dry. They're very clean and they're very portable. They also tend to heat and cool a little quicker than a typical bath equivalent. So those are some of the quick pros of a dry well and using them in your process. Some of the sources of error you want to consider with a dry well is immersion. So immersion is how far you can get either your reference probe or device under test, which I'll typically call out as a DUT, in the well, because again, there are different considerations as far as stem conduction, gradient errors, hole-to-hole errors, things that we'll touch on as we get further into this. But again, there's a few things to consider. So again, hopefully we touch on all of them. And again, as we're going along, if I pass by something too quickly, please type in a comment and we'll address it as we come back around. We'll also kind of look at a display accuracy, temperature ranges, and how that can play into the display accuracy. Stability, we'll talk a little bit about the uniformity of radial and axial, and then loading, and then the DUT or device under test sizes. So let's first talk about immersion. So most dry wells are calibrated with what they call a full immersion. So when we're actually calibrating the device or the dry well's display sensor, which you can see here, it usually resides in the bottom of the well. So we'll put our reference probe fully immersed as close as we can get it to that sensor, and then perform the calibration on the actual dry well, and then make the offsets as needed. So again, if you're using the display accuracy, you would want to get the device under test as close to that sensor or within that well as possible. Again, this helps reduce any errors that can be, caused from being too short in the well, or again, as we go through this, you may be from one side to the other, but again, we'll talk about that as we come into them. So again, with the immersion effect, you can see here, I've got an example of using a dry well with a reference. So we've got a device under test, a reference, and then our dry well's display. So this is a really, really good way to do things where if your probe or device under test is not long enough, or it's got a different size, or you've got a sizing constraint that causes you not to be able to fully immerse the probe. So if you look to the far right, I have kind of an example of how to use a dry well with a reference where they both, again, are not fully immersed. So at this point, the display setting of the heat source or your dry well just becomes a nominal set point, and then your reference would be true temperature, and then you would take your data from the device under test. One thing to note, in our newer what we call metrology wells, that's this unit down here, we do have what we call a process option or reference options built into the units. So instead of having to have an external probe and readout, we actually can build the circuitry all into one package there. So that gives you kind of the one up over just having the display accuracy or having to carry a second piece of equipment out into the field. So kind of a good one package meets all the needs there. Good rule of thumb as far as immersion depth. I've heard several over the years, but you're usually pretty safe if you take 20 times the diameter of the probe. So whatever your probe is, just multiply that by 20. So again, a 1/4 inch probe, I think comes out to be about 5.5 inches, somewhere around there. But you're usually pretty safe with that. And we'll talk about that a little bit more as we move forward here. The reason for the immersion depth being a concern is basically stem conduction. So it's basically your probe acting like a heat sink. And sometimes as you're at some of the more extreme hot or cold from ambient, you can see these errors come through in your readings. So again, probe diameter, length, and immersion kind of all play into that. And again, the good rule of thumb is 20 times the probe diameter. And that is kind of the rule of thumb for what we call a traditional platinum wound sensor. You can see here in my example to the right, we have a thin film RTD. So it's a completely different makeup. It's not using a traditional platinum wound sensor, but more so just a thin film. It's almost like a printed IC for the sensor. And you can see in these cases, the immersion depth is much less impacting as far as that versus a traditional. Now with this type of sensor, it's kind of similar to a, what are we going to call it, thermistor, where it's fairly small bead. But again, I guess when you're thinking of stem conduction immersion, more is always better for the testing. All right, so let's get into some contact errors here really quick. Just 1 second. All right, so fit is very important As we talked about the dry wells having either fixed blocks or inserts, you notice that there was a lot of different sizing options, and fit is very important. Having a sensor in a well that's too big typically results in some sort of a insulation or a low reading. And having one that's a little bit too tight usually gets your probe stuck in the unit there. So for most, for example, a 1/4 inch probe, most of the holes are drilled about 0.01 larger, somewhere around the neighborhood of 0.265. And that's usually enough to allow for some thermal expansion of most stainless steel or Inconel sheath probes without losing or getting too loose of a fit, but again, allowing enough room to get a good contact and get a good reading without getting stuck. All right. All right, so let's talk about the dry block display accuracy. With most, usually the manufacturers will give a 1-year period. You don't want to just buy one and assume that it's going to work accurately forever, especially if you're using the display to calibrate. That said, if you do have, say, an external reference that you're using and maintaining as your standard, then the heat source can be just that, a heat source. But again, if you go that route, you want to make sure your heat source is functioning properly regarding stability, and it's not giving you some other error that you're not aware of. So again, with the display accuracies, one thing to kind of consider there on my second bullet point is with the units with the removable inserts, the actual control sensors of the dry blocks are a sensor, an RTD sensor. They're usually a 385 sensor, and they are a wound sensor, so they are susceptible to physical shock or vibration. So with some of our hotter units, some of the metals that are used are brass, bronze, they can be a little heavy, so you do not want to just put the insert into the well and allow it to drop down. You always want to gently place them in there, and this helps preserve the display accuracy of the unit for a longer period of time. The other thing to note when you're reviewing display accuracies is look at the temperature range. Sometimes display accuracies do vary with various temperatures. So I did give a side example here on the left, basically from 35 to 100, 100 up, and then 225 to 420. So you can see as you go up in temperature, we are also taking an increase in our uncertainty to the display accuracy. All right. All right. Now we're going to talk a little bit about the dry block stability. So again, same thing here with the accuracy. This is usually specified, and again, it can change with temperature or temperature ranges. So again, that's my second bullet point, showing how a specific dry block may be really stable at some of the lower temps, but as we increase up in temperature, sometimes you give a little bit of that up. So again, be aware of that, especially when if it's critical to your measurement. Most units will come with an optimized proportional band in their controller setting to from the factory. So you really don't want to mess with that. Usually there's enough R&D that goes into the wells that you don't need to adjust those, or it's not recommended that you do adjust those. But again, if you're taking a reading and you can't get the results to settle, that's one thing to check is your stability, and see how that see if that's a potential source for error for you. And I do apologize if I jump a slide or two. It looks like my arrow keys have decided to take a break for us, so I'll try to gently do this with my mouse. All right, so we're going to speak briefly about the axial uniformity. And so this is basically bottom to top or top to bottom along the measurement zone, or where the heat is actually coming in. So what we've done in a couple of our units, we spec what they call an axial uniformity, where we give an actual uncertainty based on full immersion up to, I believe it's 40 millimeters up from the bottom. Some manufacturers do not offer that, and so you have to assume full immersion is what they're speccing off of, or you would want to use a reference and have that at the same immersion as your device under test. So in the example here to the right, you can see there is a potential gradient error if you have a very short sensor versus the control sensor of the unit down in the bottom. And even with a unit where we've spec'd out a axial uniformity, you could still have some potential error if it falls outside of this. So in this example, you definitely would want to use a reference probe. All right, and then the other item to consider is the radial uniformity. You may also hear this be expressed as hole to hole, so the difference between one hole to the next. Sometimes this varies depending upon the hole sizes. That can be an issue, but it's not as big of an issue. But if you're, say, going, some inserts have a half-inch hole to an 1/8 hole, you can get a bit of a hole-to-hole gradient. And again, same here when you're reviewing these specs. Most of the specifications, whether there be the display accuracy, the stability, or radial uniformity, axial uniformity, they all can change with the temperature. So again, very hard to find something that's consistent across the board from its minimum temperature all the way to its maximum temperature, and that's just due to the nature of all the changes that are happening within the unit to try to heat or cool, and then fighting the ambient conditions. All right, another one that most folks kind of overlook is loading. So again, this is how many pieces you put into a unit at once. On our new metrology wells, we do kind of calculate for this. So we've kind of said, okay, if you use 4 1/4-inch probes, one reference and 3 devices under test, here's what you can expect. And you can see it's fairly small. It's about 6 milli-K. But for some applications, like some of these transmitter heads, I've seen them get as large as 3/4 of an inch or bigger. Sometimes that can actually give you a little bit more of an error depending upon, again, size and stem length. So something to be aware of. So again, if you do have a 1/2-inch stem on something, probably best to get a larger dry well versus a unit that can take that, but then you've got 6 inches of stem out, and then you're also overdriving or probably putting too much on the little block assembly there, the mass that's trying to control that. So again, just other little odd things that we've noted over the years. This slide kind of is getting into a little bit of the calibration or uncertainty analysis. Let me jump here. Most folks, when they're combining various uncertainties, whether it be your stability, your loading, your reference, uniformity, they'll do a root sum squared method. If you want to go linear, you can do that, but that usually nets you much larger uncertainty, and that assumes that when errors happen, they all happened at the same time in the same direction. So it's kind of not practical. So the root sum squared approach typically is more common to use. It tightens up your uncertainties and kind of gives you more flexibility as far as your uncertainties and being able to tighten those up. And again, I've not seen anything unless you've knocked it off the table where everything happens at once and shifts all at once. So again, just keep that in mind. All right, and then this next example, I threw this in here just to kind of show you what the next jump is. This is actually a GUM compliant example, but it's taking kind of that next step from, okay, I'm just looking at the bare minimum of what I need to consider, and this kind of shows you all the uncertainties that go into something that's more in line. If you're trying to get accreditation, you've really got to kind of dig in at your various test points and all of the potential errors. So again, just wanted to throw that in there for some folks that may be kind of on that cusp of going down an accreditation route. All right, so let's address odd shape probes. This all kind of depends around the oddity. I've had some folks where they've got bolt-on sensors or different things, and we've actually designed custom inserts for them. And I had one that was really uniquely shaped where we actually had to take two inserts, split them in half, and then mill the insides to make kind of a clamshell that fit around this unit, because you couldn't use a bath. So there are workarounds. Usually if the DUT is, that extreme, most folks will consider a bath, but there are those times when a bath is not going to happen or it cannot be used. So there are workarounds. It does add a little bit of uncertainty when you go that route, but again, it can be worked around. Most dry wells, though, will come with some sort of a standard block design or insert. So down there on the left is kind of more common what you would see regarding typical size. Usually we've got our standard sizes and metric sizes to choose from. All right, so in reviewing a little bit more of the dry wells, again, we talked about stability, uniformity, all that. They're great in as far as a usable range. We've got them available from -95 all the way up to 1200 C. Depending upon your application, you may need to use multiple wells. And again, too, depending upon your application, you may have to switch between potentially a dry well and a bath to get the uncertainties you need or to make the testing appropriate for what you're doing. So again, as you're looking at a dry well for consideration, again, be mindful of all the stability, uncertainty, accuracy, and the temperature range as well, to ensure that you're getting what you think you're needing, or you want to ensure that you're getting what you need for the application. All right, dry blocks versus liquid in glass. This is kind of a no-no. I have had some customers that do it. That said, usually the tick marks on the liquid in glass sensors are fairly large. The big issue with a liquid in glass thermometer in a dry well is typically the stem of the thermometer is larger than the bulb of the mercury. And so what happens is you get a nice air gap around that mercury stem where you're trying to take the reading from. Again, it kind of results in a low reading. Also, the EPA is kind of putting the kibosh on them. And so again, they're kind of on their way out, and kind of digital is the way we're moving forward. All right, now we're going to get into a basic example of a 3-point calibration. Here we're utilizing our 9190. I thought this would be a good one because we can go pretty cold to fairly warm. Basically, to do the cal, we're going to start the unit. Usually you want to work cold to hot. We're going to put the DUT in with our reference, run the unit down to temp, allow for it to come up and stabilize. And then typically you want to run about 30 samples at each point and then average them. And then you move to your next point, say -95 to 0 to 140, average the data, and then you can utilize a tool like the software we have, which is Tableware, to kind of calculate the coefficient. Or if you want to do it manually or in a spreadsheet, you can do that as well. A little more difficult that way. All right. This is just a quick example of our tableware software where you can take the reference temperatures and then collect the data. And this is where I was talking about. Some folks will do temperature to temperature comparisons and do a direct offset. Or in this one, I set up this screenshot to show kind of a temperature of the reference to the DUT ohms. And then we would take this data and crunch the numbers and come up with our calendar Van Dusen equation. All right. All right, and this process actually can be automated. There's software that can do this. The one thing we have on our side of the fence that can automate it is our 1586 DAC thermometer. It's got built-in software. It drives most of our drywalls and baths. So you can actually go in, set the units up, and then pre-program the data points with your stability and just let it go. It saves you a lot of time. You just come back, grab the data, and then crunch the numbers. So again, there are a lot of options depending upon your testing process, your throughput, how many units you need to test. So again, you can go from your drywalls being a quick check of onesie, twosie, all the way up to full-blown automation, where you can save a lot of time going that route versus doing it manually. So again, it's always good to have a quick discussion with one of us on the application side of the fence, just to make sure we're not overlooking something or could save you time and money, basically. All right. And then on our website, we also have some other things if you want to kind of follow up on as far as automating testing. And then we do have a lot of web application notes on our web for various calibration examples. So again, feel free to check those out. And let's jump into our last few slides here. A couple more, Nicole. So
okay, sorry, I'm ready to jump in. I thought you were done.
No, that one I think is a little probably out of place, but that's all right. As far as some maintenance, again, with the dry wells, the blocks are usually made out of some sort of metal, usually aluminum, bronze, brass. They do oxidize with time and use. What actually works really nicely is if you get a gun cleaning kit, you can clean the wells out really well. Again, another tip is to avoid dropping the inserts or heavy things into the well. This will, again, shock your sensor. For cleaning the outside of the inserts, Scotch-Brite works really well as on that. Sometimes I've seen them get fairly corroded over the years, and if you do, you can go to a light grit sandpaper. Usually I'd stick to 600 or so. Don't get real aggressive with it. And then again, just recalibrate regularly if you are not using a reference, and always watch your stability. So again, just in close, Drylox are a great option for a quick heat source. There's a lot of temperature range to choose from. And again, if you need it, you can get the ones with the built-in references. And again, a lot of different insert options as well as range options. So again, usually we can get you fitted out for one of these that's the best fit for you, depending upon your application. So again, you've got options there to consider. So just don't think that it's a one size one application. We've kind of tried to make some flexibility as far as the market out there and various applications on that. So again, I think that's about it for me. Nicole's hosting here, so if you want to know more, there's her information. And our Transcat guys could always get us pulled in to quick consult.
Thanks, Travis. So that concludes our presentation portion of the webinar, and we're now moving on to the question and answer session. And as a reminder, if you'd like to ask a question, you can send it through the question box in your webinar controls on the right side. Okay, so let's move on to our first question. Let me see here. Hi, if a unit under test is odd-shaped or does not fit completely, can we place insulation on the end of the block or well?
I've seen people do this, so yeah, you can do that. The bigger question is the odd shape is, again, the immersion. How far are you getting it down in there is the bigger concern. Because even though you're insulating from the top down, if you've only got, say, a few inches into the actual heat source, that's going to be the bigger concern for the heat getting conducted properly to that sensor.
Okay. Same gentleman. Would that help reduce thermal conduction from the probe shaft if it's too long?
Yeah, I've seen people insulate their probe shaft, and that does help.
Okay. How often do I need to calibrate RTDs?
That's kind of a loaded question. It all comes down to your process and a risk versus recall is how I advise most people. Again, how critical is the uncertainty? How much typical shift may I see in the process versus what's going to cause a catastrophic rework or recall? So again, you kind of have to weigh that versus the uncertainty.
All right, how long does it typically take to calibrate an RTD with a dry block calibrator?
That depends on your temperature range. So in the example I gave where we just did a real quick 3-point, usually the biggest time is the movement between temperatures. The 9190 fortunately moves pretty quick, but to go top to bottom and then back through it again would usually be a few hours.
All right, next question. Can I use a drop of oil in the well for better contact?
I wouldn't recommend it. There are thermal pastes and grease out there, but unless the well is specifically designed for that, I would avoid it. What happens over time is that typically whatever makes the oil viscous or lubricating, it cooks off over time and it becomes more or less like a glue. And I've seen over the years many inserts get stuck or probes get stuck due to this.
Okay. How many sensors can be calibrated with the 1586A?
If you go with the max setup, it'll do 40 thermocouples with a reference or 24 wire RTDs with a reference.
Okay. Next question, is the 9190A only used to calibrate RTDs?
No, again, it's just a heat source, so it can be used for RTDs, thermocouples, TCs, other sensors. Again, it's just designed to be a stable heat source with a usable range of minus 95 to 140 C.
All right, next question. Can I use a PLC to control the temperature of my dry block?
Yes, so most of our dry blocks that we manufacture come with a full, basically serial command. And so if you've got something where you're interfacing, you can interface with them and use remote software. A lot of folks use LabVIEW. We also have our calibration software, as well as the 1586 does have drivers to drive most of our dry wells and baths.
Okay, next. We use a Fluke 724 and a Fluke dry block to calibrate our RTDs. The RTDs are the standard 3-pin connector for use with a female connector. Does Fluke make a set of cables with banana plugs on one end and female RTD connectors on the other to make measurement of multiple RTDs easier?
We could look at it. So on my side of the Fluke fence, I'm part of the Fluke Calibration group, so the 724 is not kind of in my product offering, but you can get custom cabling done. Again, with most RTDs, you're working in resistance, so you don't have to worry about shorting something or blowing something up because you're not applying a voltage or millivoltage. So again, if you can get the connectors, usually the large banana clips or banana jacks will work with the 7 series on the Fluke side. And then I would probably recommend with the female side, I'd have to actually see the picture of what you're working with and what the challenge is, and kind of make a recommendation
Okay.
from the hip without seeing what you're up against.
Okay, why use the 9190A over a temperature bath?
Again, it's portability. So again, a lot of folks will use the drywall over baths because either they're working in situations where they have to move around a factory or they're moving above elevation. So a lot of folks don't want hot or cold fluid above particular applications. So again, it's just fitting the kind of your process or your application need to the product. So again, you can do everything with a bath that you can with the drywall. But again, sometimes that's not convenient to pack around a few gallons of oil or even a few liters of oil to, with it. Again, typically when you're using fluid, there's a little more considerations about being fixed in a lab or somewhere versus going mobile.
Okay, that looks like our last question. I'm just waiting to see if one, oh, yep, Travis. Someone said thank you, Travis. Okay, so that's our last question. That concludes our time for today. If you have further questions or if you have a question that didn't get answered, you can feel free to reach out to me at nvanwert@transcat.com. You can call us at 800-800-5001 or visit us at transcat.com. Thanks for joining us today. We hope you got something out of the presentation and that you continue to join us for future Transcat e-learning webinars. Thanks, Travis.
No problem. Bye, everyone. Thank you.
Bye.